Hello, my name is Felix Kosmalla, and today I'm going to talk about how interactive projections can be used for agility ladder training. This is joint work that I have done with Fabian Hupperich, Anke Hirsch, Florian Daiber and Krüger from the German Research Center for Artificial Intelligence. Agility and coordination are basic skills that every athlete should seek to improve. These abilities are beneficial and are required in nearly every sport where athletes have to make quick decisions depending on their surroundings, for example when playing basketball. A common method to improve an athlete's agility and coordination skill is the use of a so-called agility ladder. An agility ladder in its simplest form is a rope ladder that is placed on the ground. The boxes between the rungs are used as stepping targets for a range of stepping sequences, varying in complexity and thus providing tools for all skill levels. The most common way of learning those exercises in a training session is by an expert demonstrating the sequence. However, a trainer might not always be available because they are supporting others, monitoring the group, or simply because the athlete is training alone. Interactive training systems have shown to be able to fill this gap in other sports like slacklining, rehabilitation, or general movement training. The aim of those systems is to allow for self-sufficient training independent of a personal coach. To the best of our knowledge, agility ladder training using interactive projections has not been fully investigated. Our goal was to implement a training system that uses interactive projections that guide users through their training. We started with a physical agility ladder in our lab. To project on it, we used the Kinect and the Microsoft Room Alive toolkit in combination with Unity for projection mapping. This allows for an easy implementation of visuals. You can see the results on the right, showing the floor of our lab, including the augmented physical agility ladder. To make it interactive, we added reflective clusters to the participants' shoes so that they could be tracked by the OptiTrack system. After aligning the real world to the virtual one, the system could detect correct and incorrect stepping sequences. We implemented a simple level system which would guide the user through the process of learning a stepping sequence, where the focus was on performing the exercise slowly and precisely. In the final level, the user was challenged to perform the exercise as precisely but also as fast as possible. In addition to the projection on the floor, we also implemented a visualization in front of the user, which is mostly identical to the projection on the physical ladder on the floor. We added a virtual representation of the ladder as well as the feet of the user, which move in accordance to the user's feet. In an initial study with 12 participants, we investigated the effect on training performance of two different visualizations. In the first visualization, we projected directly on the agility ladder, while in the second, we projected the guidance on a big projected screen in front of the participants. We chose a between-subject design, splitting the participants into two groups. The task was to undergo 2 training sessions in which they practiced with the system. We measured the NASA TLX score as well as the score of the Illinois agility test. In this test, the participants had to run a pattern as fast as they could. This was set up in a nearby gym, as seen on the right. The participants had to run the score 3 times, where the fastest time was taken as the resulting score of the test. During the course of the study, that was split over 2 days, the participants first started with the preliminary questionnaire, asking demographics and training habits. In the first test, we assessed the agility of the participants before the first training with the system. After that, a NASA TLX questionnaire was provided, followed by a second agility test. On the second day, the participants underwent the same procedure with an agility test, a training session, the NASA TLX, and a final agility test. Then the participants were allowed to try out both visualizations so they had a chance to compare them. Their thoughts and opinions were retrieved in a semi-structured interview. We could find a significant improvement in the agility score, but only in the wall projection group and only in the first training session. Comparably, the wall projection group scored a higher mental demand in the second training session. Additionally, we could observe more failed repetitions in the wall projection group. After trying both systems, the participants stated that they generally enjoyed training with the floor projection. 9 out of 12 participants could imagine to continue with the training since they liked the fact that they could train independently of a human trainer. 11 out of 12 participants preferred the floor projection over the wall projection in front of them. 3 participants requested more varied exercises. In conclusion, we implemented an interactive agility ladder trainer with 2 different visualizations. The user study showed that the system is a fun way to train agility. Since we only had 12 participants, we can only suggest that a projection on the wall might increase the training effect. Looking at the favored floor projection, a combination of both visualizations may be beneficial. In the future, we plan to increase the number of participants, at a baseline with the human trainer, and experiment with other visualizations.